Hi everyone. So I'm just making this quick video to demonstrate the technique that I would like you to try to use to get the uncertainty in your E over M value in the lab that's due the next time I see you, the next lab I see you. So this is roughly what I expect your data should look like. Okay, this is just data that I created for the sake of the example. You should have somewhere between 6 and 8 data points running from, well, I've been bad here and not labeled my units, but you get the idea. Between 200 to 500 volts, and then you should have found and recorded the currents that that was running through your system, such that the radius of the trajectory of your electron beam remained constant, etc., etc. And then you're asked to graph that as a graph with the voltage on the y-axis and the current squared on the x-axis. So I've just kind of recreated this data. I've just done created a formula. This is just the square of I here. So first things first. So this is standard what I think I went over in class for those of you who had seconds I was there for. So I'm going to I'm going to select my data and I'm going to insert. I want to insert a scatter chart. Good, that's about right. And of course, when you create your beautiful graphs, you'll give them nice names and such, but I'm not going to do that. Okay, so what we did to find D over M, if you remember, is it involved finding a trend line. So I just added the trend line here in Excel. I'm going to click Display Equation on Chart, and you'll see, and I'll drag it just so it's a little easier to see. You'll see that the equation that best describes my data here has a slope of 300, and let me zoom in, has a slope of 339.82, and that's in units of volts per amp squared, I guess, with a y-intercept of 2.3146 volts. So that's all well and good, and that's the slope value that you actually are going to use to calculate E over M. But the interesting question today is, how do we find the uncertainty in that slope? So in 1125, we used to draw error bars, and we would have a best fit slope and we would have a worst fit slope. We will be doing something different today, okay? So in some cell, anywhere you would like, we're going to use this very particular function. So I'm going to click equal. I'm going to go up here, and I'm going to type the following command. Line, see, it's already suggesting it to me, st, okay? Looks like the word linist, not that that's really a word. So, luckily, depending on what version of Excel you're running, that being said, remember that you can always download like a fairly new version of Excel via the college website, and or use our computers here. So it tells us, if it's a new enough version, it will tell you what to input. So it says here the first thing that this function wants is our quote-unquote known y's, okay? So of our data, what are the y values that we know? So we're plotting voltage as our y values. So I'm going to select my voltage data here, okay? And now it wants me to put a comma, and now it's prompting me to add the known x's. Well, these are my known x's, my x values, okay? The next two are two optional parameters that you need to provide. So here it says, right, either I can put false or true. If I put false, b is set equal to 0. So if I type in the word false, this is going to force my y-intercept to be 0. But we don't want that. I mean, we've already seen with the trend line, the y-intercept, at least for my data, actually for everybody's data, it's very unlikely it's exactly 0. So we're going to click true, or type to true, I mean to say, and that will calculate the b value normally. And then our final one, this is important, is stats. So this is what we're actually using this function for, is to get some statistics about our best fit line. So we're going to put true here because we do want this to return additional statistics. I'm going to close that out. So my command looks something like this. Yours should too. Of course, you might have your data in different columns than E and D. That's all right. You might have slightly different number of points. I'm going to click enter or return. Boom. And it's going to populate a whole bunch of cells here with a bunch of numbers. So let's take a close dive. Most of these numbers we can ignore. Let me just drag this over a bit here. So the first top two numbers that this function will output should look familiar to us, right? So these two numbers are these two numbers. They're the two actual parameters involved in the fit. In other words, this is another way of just getting the slope of your best fit line, okay? You don't need to add a trend line and like read it off of what it produces. You could just use this function. It will tell you in this first box what the slope is. This is going to be the y-intercept. Now the only two, okay, I can tell you right now, we don't need any of these bottom four, so I'm just going to clear those. Actually, am I even able to? Oh, maybe it gets mad at me. Okay, well, let's just ignore them. Oopsies. Ignore. Okay, so we really, in fact, we can ignore that guy too. Really, the only ones that you care about are these, and really not even all of these. In fact, mostly just these three. Actually, let's say exclusively these three are going to be the ones that you care about, okay? So the slope, because we don't really care about the y-intercept. The slope, the number directly beneath the slope, and this one is just interesting, okay? So this second number here is really of interest to us, okay? This is the quote-unquote standard deviation of sorts on our slope. So when Excel runs this function and produces the best fit line, it performs a whole bunch more statistics related to something known as a least squares method, regression, okay, where it tries to find the best fit line, and it produces this number as basically the uncertainty. So this does it for you. This tells you that the slope of my data in particular is 339.8 yada 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 plus or minus 5.77. Okay, so it's as easy as that. Right beneath the parameter, i.e. right beneath this slope parameter, Excel spits out the uncertainty in that parameter, okay? So when you want to know what the uncertainty in your slope is, that is how you're going to get it. Oopsies. I guess just so you know, I know I covered it up, but this too is the uncertainty in the y-intercept. So you can see actually the y-intercept is like horribly uncertain. Given that it's only 2.3, it's plus or minus 6, so not so good, but it's not important for our calculations. This third thing, which I said is of interest, this is something known as an r-squared value. So we're not really using it today, but in statistics, an r-squared value basically is a measure of how good your fit is, how close it is to being truly linear. And if it were perfectly linear, if my data were in fact perfectly linear, they fell exactly on a line, this r-squared value would be equal to 1. And the closer to 1 that it is, the closer to perfectly linear your data is, and the better job you've done at fitting your data. So with a value of 0.997, my data is very linear, but that's also because I faked it for the example, okay? Although I could have made it perfect, but I chose not to. So yours might be a little bit lower than this, and don't worry, it's just interesting. So, as long as this is above, 0.9, you would hope, but it's not the end of the world. If not, then you're golden. But basically, this is how we are going to find the uncertainty, oopsies, in our slope. That's all I have for now. Thanks.